Good morning, everybody. It's 9 a.m. here in San Diego, so we will begin today's webinar. Thank you very much for joining us and for your support of the webinars. Is on structure and ligand-based docking for lead design and optimization, focusing on the ligand docking tools inside the ICM 3D Ligand Editor. This is a part 2 of a three-part series on the Ligand Editor. Ms. Andrew Ori, and if you have any questions during the webinar, please the chat. I'll try to get to those either at the end of the webinar or to you via email. If you have any questions after, you can also email me or call or email info@molsoft.com. The recording of the webinar will be placed on YouTube, and you can see other webinars there as well as other training tutorials. We also have manuals here. You can also, there's some papers that I'll be talking about, publications. If you want a copy of those, I can get one for you. Just let me know by email. So if you're not familiar with MolSoft, we're a San Diego based again. Max Tochra, principal developer, and Polo Lam is a senior scientist here as well. And we're founded in before long-term collaborations with Big Pharma and a variety of different other companies. You'll see that our product is called ICM. ICM stands for the coordinates that we use, which is internal coordinates, and ICM stands for internal coordinate mechanics. And the docking is based on a method developed by Ruben and Max called biased probability Monte Carlo. And we'll also be looking a little bit at the 3D pharmacophoric fields. You can dock to a protein receptor here, or you can dock to 3D pharmacophores. So the 3D Ligand Editor is incorporated into ICM Pro, as well as ICM Chemist Pro. ICM Pro contains the majority of the molecular modeling tools that we have. It's our main desktop modeling software. And ICM and other tools can be placed inside this environment. So we have ICM Bio, which is a full bioinformatics tools panel, set of software, including like the sequence alignments and linking sequence alignments to structure, which is useful for mapping differences in families, if you're looking for specificity, for example. We also have a wide range of cheminformatics tools, from reading in chemical spreadsheets to calculate multiple parameter optimization, things like blood-brain barrier, and in ADME tox properties of chemicals and things like that in ICM Chemist, and tools for building combinatorial libraries, and also exploring SAR, identifying activity cliffs and things. So most of our customers, they have this as their, and then they can share everything you do in ICM. So your docs complex, you can share using iMolView, which is a free download for Android or Apple mobile devices like iPad. And we also have ICM Browser, which runs on Mac, Linux, and Windows. And you can also share your data on the web page using ICM JavaScript. Some new tools that are available are here as well. MolScreen is a library of is a set of many drug candidate targets with built-in models, so you can run one or more ligands against this panel and see which other targets your ligand may hit. MolCart GigaSearch we developed in collaboration with Enamine. They have Enamine has the real database, which is a billion, more than 1 billion chemical database. It's very large. We developed an efficient way of substructure searching that database. And if you have the free 30-day license, you can search Enamine, the real database, directly in ICM. And last year we released a method called RIDE, which is a base screening, which is extremely fast. It can screen 500,000 chemical conformations a second per GPU. It can be used for virtual screening, scaffold hop. These are available in this one single. So if you missed last week's webinar, it's on YouTube if you back at it. But it goes into more details about how to set up the ligand and receptor for editing in the 3D Ligand Editor. It has description of display options there and other things. But today's webinar, we're focusing on if you want to redock it to make sure you have the right ligand use. Then we're going to cover ligand docking, docking to a template, docking using distance restraints, and docking using tethers. We're going to look at how to incorporate flexibility into your receptor during docking, different methods that are available for that, covalent docking, and also docking to 3D pharmacophoric fields. So if you don't have a crystal structure of your protein, but you maybe have some good activity data, ligand-based activity data, then you can use that to design or optimize your lead compound. And in a couple of weeks' time, we're going to be looking at some of the more kind of advanced uses of the Ligand Editor for things like core replacement, PROTAC design, isosteer search, and searching larger databases for virtual screening. So the 3D Ligand Editor itself was developed in close collaboration with scientists at Novartis, and the tool is basically a 2D or 3D environment whereby you can make changes in 3D or in 2D, and then so you can just click in the 3D environment and delete atoms or make modifications. And then you can also, everything is fully undone. You can undo and redo. And there's a full suite of tools for group replacement, heteroatom scanning, and isosteer replacement. So the docking method that we have is described in these early papers by Ruben and Max, and basically uses the bias probability Monte Carlo method with local gradient minimization to optimize the docked ligand's internal variables. So there's a fully flexible ligand, and it uses the Monte Carlo simulation to globally optimize a set of internal coordinates of the ligand in this space. So in this grid we have here shown in green is the grid where the ligand will be docked. The pink is the protein receptor. So in terms of docking, initially the first move is a random move to one of the rotational, translational, or conformational variables of the ligand within this pocket here. Then energy functions are minimized, desolvation energy is calculated, and then we have a criteria called the Metropolis selection criteria, which is used to determine whether you want to accept or reject the conformation of that ligand that it finds. And this procedure of randomly sampling the ligand inside the box is repeated until a maximum number of steps is achieved. So the length of the simulation is actually defined by a value called the thoroughness value. You'll see an option called thoroughness. Sometimes it's called effort, but basically that is the length of the simulation. So generally, the default values for effort are fine for just single ligand docking. But when we show you some more advanced flexible receptor docking, that effort or thoroughness needs to be increased a little bit more in order to thoroughly sample the energy landscape of the protein. So for example, for flexible receptor multiple conformation docking, inside this grid, pre-calculated grid maps, which account for hydrogen bonding potential, van der Waals interaction, high potential, and electrostatics. And so basically, so this is basically describes the method that we use. If you want to read, I can send you the original papers or more recent ones on the docking approach. So in the last 3 years, or from 2017 to 2019, each year there was a docking industry-wide docking challenge called D3R. And in each of the 3 challenges that we competed in, 2, 3, and 4, in 2017, MolSoft ICM outperformed other methods that were in the competition. So in 2017, the prediction was to look at FXR ligands and predict the binding affinity of 102 other ligands. MolSoft's submission ranked RMSD in terms of redocking, and it also ranked first in terms of binding energy prediction as well. In 2018, the challenges larger scope and MolSoft ranked first place with docking pose and binding affinity for all these targets. And then in 2019, the challenge was a bit different because it was the ligands were macrocycles. So it was an interesting test, and ICM accurately predicted the pose of the EACE macrocycles in this challenge as well. You can read these publications online. I can send you these papers basically by Polo Lam at MolSoft and Ruben and Max Totroff. So once you dock the ligand, you get a score. So, and the score is you'll see when we start docking that we have 2 different scores. One called LE score, which stands for Ligand Editor score. And this score is based on like a molecular mechanics physical energy term score. It's been used for a long time in ICM. And they recently had an RTCNN score, which is the new score developed in ICM. And it's completely different from this Ligand Editor score. And it's a brand new scoring option, and it's available now in the latest version of ICM. And basically, it's using neural networks. It's not published yet, but basically, it doesn't use molecular mechanics or physical energy terms. So instead, it's trained to recognize native light complexes versus decoys directly. So, for example, if internally the neural net recognizes a hydrogen bond, it's because it was observed during training for that configuration. It's a completely different score, and it's actually performing better than our original score. So you'll see both of those scores, and you can use both of those. So in today's example, we are going to look at the ATAD2 bromodomain. Bromodomains are acetyl-lysine specific protein interactions, and they play a key role in regulating gene expression. We looked at this structure last week, but there's this paper that has the crystal structures with the complex with different ligands. So it's a useful example for the Ligand Editor. And one way of exploring potency and maybe specificity versus ATAD2 versus other members of the BET family bromodomains, is to explore this RVF, what they call the RVF shelf in this region of the protein. And there's also a region here to explore, to build upon in order to add potency to these ligands. So last time I showed you in the YouTube video, you can go back and you can see the individual steps for setting up the receptor and ligand. So I'm going to do that quite quickly in this webinar. And I also just want to that everything you do in ICM in the desktop version can be done online using ICM JavaScript. And so this is basically a web page, and you can do the docking directly inside the web page, which is sometimes more convenient rather than downloading the software. Okay, so I'm going to move to ICM now. So in this example, I've read in the bromodomain protein with the PDB code 5A50. And you can see here that we have it's an X-ray structure. It has 2 angstrom resolution. It has an A chain and a protein ligand bound. So you can see the ligand bound here, and we can zoom in and we can look at the interactions. If you wanted to, just go here, right click on the pocket and say ligand pocket interactions, and you see the interactions. So how do we, we're going to start, how do we make some modifications and dock those? So to do that, we need to use the Ligand Edit tab, which is shown here. And so we click on the Ligand Edit tab. And from last week, you probably remember that we have to set up the ligand and the receptor using these 2 buttons here. So we just tell ICM which is the ligand, which is it has the code AJ5I, and then we go to the receptor, and we have some questions regarding the receptor, what we want to. So I covered this last week, but I'll just quickly go over it. You can choose to keep waters that are tight in the pocket, making 3 to 4 hydrogen bonds with the ligand and the receptor, or you can keep all the waters in the pocket, or you can assume that the ligand displaces all the waters, and so you delete the waters. The next questions are related to the protein itself. So whether you want, and that's actually the waters if you leave them. So it's a PDB file, so we're going to add hydrogens to that PDB file, and so we can optimize. You can add the hydrogens. So you should check the option to optimize existing hydrogens, optimize asparaginins and glutamines and histidines in terms of the hydrogen bonding network. And in cases of low resolution structures where you don't have full occupancy of the side chains, you can either mask them, and so there will be a gap there where there's no atom, or you can uncheck here. ICM will build the full atom model of that side chain. You can then identify ligand binding pockets. You can run the ICM pocket finder, and it will find cavities around your protein. But in most cases in the Ligand Editor, you're starting from a position whereby you have a ligand bound already, so there's not really any need to identify the pocket as such. But you may want to be able to differentiate the allosteric site or some extension to this pocket. It could be useful to run it here. But in this example, we'll just choose the option make box around existing ligand. So you can see now we have this purple box, and so inside this box is where the grid potentials will be made. It's going to make it a little bit larger, so you can just drag on the corners of the box because I actually want to expand into this region here for the redocking. So I'm just going to drag in the corners Sometimes it's a good idea to show the side chains as CPK in the display, like spheres. You can see exactly how, where you may, if you're particularly targeting a particular residue or something, you may want to just make sure that the box encompasses those. And then you just go OK, and then it builds the maps. And so by default, it shows you this surface, which we covered last week or 2 weeks ago. And basically it guides you as to what you need to add to your ligand, what would be a good substituent. So so here it's saying you should add a hydrogen bond acceptor at this point. Green is hydrophobic, blue is hydrogen bond donor. So we're going to concentrate on docking today. So I'm just going to make, going to edit this ligand and then redock it. So we have these tools here to edit the ligand. And I'm going to add I can try and mimic one of the ligands in that paper that I showed on the PowerPoint file. So I'm going to draw it with it has a piperidine ring, a piperidine here, and so we can just one second. So if you want to take the ring here, and then we can convert it to piperidine. Just going to add it here. So need to add a nitrogen at this point. So just click on the N. You can see hopefully you can see the panel here, different substituents. So it's going to click on N and replace here. And in the paper that has a linker here. So now the ligand is made, and we want to redock it. So we can initially just do small minimization of the ligand. So we have two buttons here, which have the left one is minimization and the right one is full docking. So if we do a small minimization, this ligand, so we have the reported score here, the RT-CNN score -21, the ligand editor score -10. But I think this pose can be improved if we did a full docking. So to dock it, we single click on the docking button, this one, and then it will redock the ligand. Oh, sorry, actually, first things first, let's undo that. I didn't charge it properly. See, we need to charge this piperidine ring. So as in everything in ICM, you can undo and redo. So if we charge it, to charge, we use the, there's a plus and minus button here. If you click on that plus and minus button, then it will use our pKa model to charge the ligand properly. So it's going to go OK, and then we'll see that this is correctly charged. So now if we redock it, and before docking, you may want to check the ligand editor preferences. So we have here a lot of different things, but probably the key one is the thoroughness. So you remember I said that the length of the simulation is based on this thoroughness value. Just for speed of the demo, I'm just going to choose 1, but I think by default we have a value of 2 or 3. It should still be very fast docking, if that's the case. Then we have an option for how many poses that you want to produce, and you can choose how many you want, but by default it's 5. And some of these other values are related to other parts of the ligand editor, but in terms of, so we just go OK, and so now if we go back to the docking button, it will redock that ligand. And we should be able to see, yeah, we have this nice hydrogen bonding network. It makes a hydrogen bond with this aspartic acid up here. We have an improved, if I just zoom in here, we have an improved score, and the Ligand Editor score is better, and the strain is reasonable. Generally, less than 5 is a good strain value. And so yeah, so we've redocked it. So other options for docking in this environment are it's going to undisplay the surface. So you may want to keep this that Thiridone ring in place, or part of that ring, this ring in place while you're docking. And so to do that, we have some options called tethers or distance restraints. I'm just going to zoom into those buttons. So the D is a distance restraint, the T is a tether. So if we click on the tether button, you see it's grayed out a little bit. So it means that you can just click on the atoms that you want to keep in place during docking, and then when you redock, these atoms won't move. They'll be placed here, and you can see that you have this table come up called dock restraints. So you can choose to use one or delete one here. So or in this table basically. So here we have 6 restraints for this ring in this position here. You can also just undisplay them, but you can add some additional, play around with some additional parameters which would give that ring a little bit of flexibility to move. You'd add maybe 1 angstrom or something less than that, maximum distance to minimum distance from that point. And that gives it a little bit more flexibility if you want to try that. You can use the distance restraint. So a distance restraint is the D button here, restraints, and so set a distance restraint, you need to click on. You can put a maximum distance, the distance you want to preserve, or a minimum distance. Put 1.8. You can maybe change this to 2.1 or something for maximum distance. It's up to you how restrained you want these to be. And again, you can either delete the restraint, or you can just not use it. It's up to you when you redock. So those are the 2 restraints. A third restraint would be to use a template. So here we have from our original crystal structure, we have the template molecule, and just going to undisplay. That won't be in your the core here. We can use that as a template and dock our ligands to that template. So to do that, we would right click. We need to move. I'm just going to undisplay the ligand. So we're going to use this as the template for docking. So you just right click and then move from object, and I'm just going to rename it template. So now if you go to the Ligand Editor and you go to the Edit Tools panel again, there is this button here to add a template, this one here. So you click on here and it asks you which of your objects you have as a template, and I called it template so I can find it easily. And you can either match, when you're docking ligands to this pocket, you can either match the ligands by substructure, or you can match by APF, which stands for Atomic Property Field. And I'll be talking a little bit about that at the end of the webinar for the ligand-based docking. So you can go APF, and then you see with APF we have these clouds. So now any ligand you dock, it will not only try to match the receptor, but also try and fit it into the ligand into these clouds, the pharmacophore. So white is aromatic region, yellow is lipophilic, red's hydrogen bond donor, acceptor, blue's hydrogen bond donor. Okay, so yeah, so the three restraints you can use are all in this region of the editing panel: distance restraints, tethers, and templates. So in the Ligand Editor, you can basically dock whatever you want. You don't just have to edit the compound you have in there. You can also dock a chemical spreadsheet to this pocket. So it's a small scale virtual screening. So primarily the Ligand Editor is developed for lead optimization. If you're doing screening, you would probably use the docking menu here for sort of large scale virtual screening. And that's what the docking menu has always been used for. But for the Ligand Editor, you do have an option to dock small tables of chemicals to the table. So it's like a small scale virtual screen. So to do that, you would have to go to File. You have to open your SDF file. And let's find it. Yeah, so I have some of these bromodomain inhibitors here. It's a very small file. It's only got 5 inhibitors in here. But to dock this table, you can go to the Advanced tab and then choose the option Dock Table here. And then it asks you some questions. So the first is what table are you docking? We're going to be docking the ATAD2 inhibitors. The effort, again, you may want to increase this to 3 for regular docking, but for this example, just using 1. Number of poses per ligand to keep is 3. You could just not dock them, but just minimize them if you already have them in 3D conformations. And there's also the option to screen by covalent docking. So it shouldn't take too long to dock these 5. Once you're docking, you can see it says docking. At the bottom here, there's like a progress bar. And then you get at the end you get the table. Once it's finished now. You get a table called ligands, which are your dot ligands. You can sort by the RTCNN, the neural network score, or you could use the Ligand Editor score, but primarily now we're using this CNN score. So then to load the dot ligand, you just click on this row, or you can just toggle the ligand on and off here. So if you want to load this one, it will load into the 3D display. Okay, so that's the docking options. So we're going to go back to my slides and talk a little bit about induced fit docking. So obviously one of the challenges of docking is to incorporate somehow the flexibility of the binding pocket. So in the Ligand Editor, there's a couple of different ways to do that. One, the most efficient way is 4D docking. So 4D docking relies on multiple conformation receptors, multiple conformations of your receptor, basically. So you may have like 4 or 5, maybe more crystal structures, which kind of represent the flexibility of the pocket. So you may have one with a loop into the pocket, one with a loop out. some different side chain conformation. Before we develop this method, the way to do this originally would be to dock individually to each single receptor, then process the data, and then combine it, and then compare. But in ICM, we have this 4D method, which will dock to an ensemble of structures in one docking run. And so these ensembles are stored as what we call 4D grids. So the fourth dimension is the receptor conformation. You can read about the method in this paper by Giovanni Bottegani and Ruben and Max. And there's some benchmarking as well in that paper for this. So with this kind of docking, you obviously need to increase the thoroughness value or the effort value to like maybe 20 or something like that. So it gives it a longer in order to sample the ensemble of structures. So you can also have a receptor with a water molecule in the receptor pocket or out. It's up to you. The other method, which is called hybrid partially explicit receptor. So you could imagine that you have an environment, an example where you have a pocket which has some flexible, or one or two, maybe three or four, maybe flexible side chains that you know are going to move, or a water molecule which may be or hydroxyls that can be reorientated. So you can select side chains that can be fully explicit during docking. So you still have the grid for the majority of the protein pocket, the binding pocket, but you can select certain side chains to be fully flexible along with the ligand during docking. So let's just show you those. So I have this example. It's with the fibroblast growth factor, where we can, if you had the APO structure, the green one shown here, green, this lysine is basically inside the pocket in that crystal structure. So, so in order to dock the inhibitors to FGFR, you need to move this lysine out of the pocket to accommodate the ligand. So I can show you this. We'll show you. So here we have the APO structure. It has PDB code 1FGK, and this is that lysine that we were looking at earlier in the PowerPoint slide. So it's residue number lysine 514. So if we display the other, you can see the lysine here from when the inhibitor is bound, that lysine is shifted. So the other structure it shifts out basically. So if we wanted in the ligand editor, if we wanted to dock to this this structure with that lysine fully flexible, the way to do that would be we need to set up the ligand, which is, it could be any ligand. So it's just using one there, and then set up the receptor, and the receptor is 1FGK. Okay. Okay, so you can see when we actually set up the receptor, we get the receptor here and the ligand, they're separate objects. So we need to select that lysine residue. So the lysine residue is here, lysine 514. So it has green crosses. So we can see at the moment there's this, if we look at the energy circles, which we looked at last time, this ligand clearly clashes with that lysine. It also makes other clashes here we need to do minimization. But if we want to redock this ligand with that lysine fully flexible, we select that lysine. I use the residue selection button here, this XXA5 button. And then we go to advanced, and there's an option called define flexible receptor groups. So you could choose maybe up to 4 side chains. You can choose as many as you want, but the key is you don't want to sort of run into generating artifacts. So you want to carefully select maybe up to 4 or maybe 5 side chains. And then, so with that lysine, I want to have the full side chain to be fully flexible. There's an option just for the hydroxys and the waters to be flexible, but I'm going to choose full side chain. Go OK. And then we can redock this ligand now, and this lysine will be able to move away, come back into it to accept that, to accept the ligand. So I'm going to try and do this. So if you're doing flexible docking, you need to go to preferences and then choose thoroughness value. I'm using 1, but you would use 20 or something of that nature, around 20, maybe 30, depending on how large the ligand is in the pocket. And then go OK. And then we just redock in the same way, just using the ligand docking button. I'm just using a thoroughness of 1 just for speed in the in the demo, but it may take a little bit longer to run than usual. But, okay, so it's done. So now you can see that the lysine actually moved out of the pocket. From the original lysine is this one. So if we go through the stack of, so in this example, we have three proteins, 3 kinases. Let me just color by object, different colors. Three proteins which represent the flexibility of the binding pocket with that lysine in and out. So first, for the 4D docking, we first need to superimpose these structures. So you just select them, go to display and superimpose button. I'll just show that a bit closer. It's this one here. And it is, they're all superimposed. And so on receptor setup, we go to Ligand Editor. We choose the ligand again. And then the difference is when you set up the receptor, you need to select all the receptors that you want to include in the docking. So I want to include 2FGI. I want to include 1FGK, which is the APO form, and the 4RWR. So I select those 3, and then on receptor setup, you see in the option here it says receptor objects. And we have 3 structures that we're going to dock to in one go. So you just go OK, and it makes the maps. It takes a little bit longer to make the maps because we have 3 structures. So then I have the results, an example with the results. I'm going to open the file with the okay, so once it's set up, then to dock your ligands to the, once it's set up, you'll see these additional receptors. So this is a different example. I'll go back to this. Yeah, this is the one we were working with the kinases. So you see that now we have these 3 additional receptors here. The original ones are here. So these are called _rec. And so basically we can redock this ligand to this ensemble of structures. You click and hold on the dock and you choose redock in multiple receptor conformations 4D, and it will doctor all 4. And then you'll be able to toggle between each one and see the score of your ligand to each conformation. So you evaluate the score. The lower the score, the better. And yeah, so you can also use this for let's go undo the hydrogens. You can also use this for specificity design. You could have one receptor from a different, the receptor you're trying to design the drug for, and a receptor you're trying to avoid targeting. So you can design in this 4D environment. So in ICM, you can also do covalent